Okay, guys. So today is what, week 5? Week 5 day and 02/03/20. Okay, so what we have to discuss today, we're going to go over capacitor. We're going to look at the relationship of current and voltage across a capacitor. And then we are going to look at how to calculate the values of voltages and current if one quantity is given to you, how to calculate the power in capacitor, energy stored in capacitor, and all those things. And then we are going to use capacitor in the circuit, what we call the first order circuit, when you have one resistor and one capacitor. And then we are going to solve those circuits. All right. I think all of you know the symbol of a capacitor, and all of you have seen a capacitor as well in the lab, right? So the symbol of capacitor, either you have this or you have one side crooked. Both are capacitor. Generally, the one that have both straight lines and the one that is crooked. These are not the polarized capacitors, so it does not matter how do you connect these. You can have one side positive and the other side negative, whichever way you're connecting with the power supply. Generally, the other symbol is for the polarized capacitor, that one side has to be positive and the other side has to be negative. So this is non-polarized in general, and this is polarized. Capacitor is simply comprised of true electrical plate, the electrical material. It can be, aluminum, iron, or anything that can conduct. And then it is separated by an insulator. That insulator can be either air, like mica, paper, whatever is there. But you have insulator between the two electrical plates. Now, so when we discuss that, okay, current is passing through the capacitor, let's say current IC, and the voltage across the capacitor is VC. Let me ask you this question. If you have insulator between the two plates of the capacitor, how the current can pass through a capacitor? Because you have insulator over there. No, my question is simply that many of you and we always say, well, current passing through the capacitor, right? But it does not pass exactly. That's the answer. Current does not pass through a capacitor. So why do we say current is? So if a capacitor in a circuit, of course, current is going through the circuit where even the capacitor is. You have some current. So what happened? How come current is in the circuit if it cannot pass through a capacitor? Whether it's an AC circuit or a DC circuit, it does store energy. So capacitor stores energy in the electrical field that is established between the two plates where you have your insulator, basically. An electrical field is established from the positive side plate to the negative plate. Electrical field is represented by E, and capacitor stores energy within that electrical field. But my question was, why do we say the current is passing through the capacitor and say that current does not pass through capacitor, which is the correct answer. It does not pass through a capacitor because you have insulator right over there, right? Current cannot pass through an insulator. So what happened if you have a capacitor and you have a current in the circuit? What's going on then? Let's take the example of DC first. So you connect this capacitor to a DC source, right? Now, as soon as you connect the capacitor in the DC source, assume the capacitor does not have any energy stored, right? Like you take the capacitor from the from your bin, and it is discharged completely. There is no energy stored in the capacitor. There's no electric field, so there's no energy stored. You connect that capacitor in a circuit. You have resistors. You have capacitor, right? Now, what's going to happen initially? When you connect one side positive, one side to negative, then it starts sending, of course, running the electrons, and those electrons starts accumulating on one plate. The other plate, and let's say positive charges. Let's say positive charges start accumulating on one plate, or electrons, negative charges, start accumulating on the other plate. But when the electrons start accumulating on one plate, the same number of positive charges, or the other plate becomes same number of positive charges start accumulating on the plate which is on the other side because of the establishment of the electric field. Or you can think about it in the opposite way. Positive charges start on when the current starts flowing. Positive charges start on one plate, electric field is established, and the same number of negative charges are established on the other plate. Or don't think about in terms of charges, think about in terms of voltage. When you have electrons accumulated on one plate, then basically it establishes an electric field and a potential difference. It arises between the two plates because one plate has more negative charges and the one plate, let's say, does not have any charge, what we call absence of negative charges or positive charges. So when they starts accumulating, as long as they're accumulating, you have the flow of electrons, and current is the flow of electrons. So you have current as long as your charges are getting accumulated on the capacitor plate. Now, once the capacitor plate says, no, now I'm full, I cannot take any more charges. I have established my electric field, it's complete, and I cannot take any more charges. Then what's going to happen? Basically, the flow of charges, it will stop, and the current is going to stop in the branch where the capacitor is connected. So when the capacitor, to a DC circuit, when the capacitor is fully charged, that is when it can no longer take any more charges on its plate. It is fully charged. It has energy stored in its field in the capacitor. It has established a voltage between the positive and the negative plate, and the flow of current goes down to 0. So when a capacitor is fully charged to a DC, it acts as an open circuit because the current does not flow through capacitor. However, you do have voltage across the capacitor. So let's say you're doing a lab, you're very happy, the lab is going successful, you took out the capacitor. I was like, hey, the capacitor, there's no current going through the capacitor. You measured it, it's like, I don't have any current in the capacitor. You took it out, you short circuit the two leg, and then you will hear a pop, right? You will see a spark and it's gonna pop because yes, there is no current, but there's energy stored in the capacitor and the two legs have some potential difference between them. So as soon as you short circuit that, you have positive and negative voltages, and the energy is going to dissipate through the legs, through the capacitor, and you will hear a big pop, and capacitor might burn as well. So you have to be a little careful when you're dealing with capacitors because you are dealing with energy storage device. So the answer is current does not flow through capacitor. Current basically is the flow of charges. So as long as the charges are flowing in the circuit, whether those charges are the one that are accumulated on the capacitor plate or any other charges, then the current is flowing in the circuit. For AC, of course, since your voltage is constantly changing for AC, so the capacitor will keep charging and discharging. In half of the cycle, it is charging. In half of the cycle, it is discharging, and then it is charging in the opposite direction, then discharging in the opposite direction. So again, the current keep on, the charges keep on moving in the circuit. Again, they're not going through the capacitor, but they're moving, right? And that's why we say the current is flowing in the circuit. But the capacitor itself is not conducting the current because of your dielectric that is between the two plates of the conductor. So that's how we say the current is passing through the conductor. It does not pass through the conductor, remember that. Of course, the unit of capacitance is farad. Generally, farad is a huge unit, so we use microfarad, nanofarad. I think the biggest capacitor we have is like 1 millifarad, if I know correct, right? We don't have anything bigger than, like 1000 micro is the biggest that we have. And we don't use that very commonly anyways. Yeah. So the bigger the size, the bigger the value, the bigger the capacitor is going to get. But not only that, it also depends on how much energy it can store and the voltage that it can sustain. So even if 1000 microfarad capacitor that we have, it may be like this big, but it cannot have a lot, you cannot connect that with a very high voltage. The high voltage capacitors that are used in motors, generators, they're pretty big and they can withstand a lot of voltage and energy. So farad is not very commonly used. Microfarad and millifarad is used. Talking about microfarad, millifarad, or millivolt and microvolt, or milliwatt, microwatt, nanowatt, please, whenever you are calculating something and the value is small, use prefixes, please. Do not use 0.00000000928 watt, because I'm not going to sit down and count how many zeros you're putting. So if it is something like that, put 9.28 milliwatt or microwatt or nanowatt or picowatt. Same goes for any value that you are calculating. So use engineering prefixes for very small or very large values, please, and make it a habit. Okay, the relationship between the capacitor current and the capacitor voltage is that capacitor current can be calculated or is directly proportional to the rate of change of capacitor voltage. So we are now dealing with the differentiation. Capacitor current is directly proportional to the rate of change of the capacitor voltage. And if you remove the constant of if you remove proportionality, then the constant of proportionality is simply the capacitor value. And this is the basic equation that relates the capacitor voltage and the capacitor current. IC is equal to C dVc over dt. So this is your capacitor current, right? Capacitor. Now from this capacitor current equation, how we can write down the capacitor voltage equation? If you have one current in terms of the differentiation of voltage, if you want to write down the voltage equation in terms of the current, what operation we are going to use? Integration, opposite of that, exactly right. So we are going to integrate both sides and we will find what is the voltage. So we will integrate IC with respect to the time. Let's say time t1 to time t2. And then and remember the V is the function of time, and then likewise I is the function of time. So we integrate both sides with respect to time, and you are going to get Vc at time t2 minus Vc at time t1 is equal to 1 over C t1 to t2 IC dt. And if there is no energy stored in the capacitor at time t1, that is capacitor is discharged. So you took out from the bin, there's no energy stored. Then Vc, of course, is going to be 0 at time t1. And you can calculate the voltage at any time t as 1 over C, assume t1 is 0, 0 to t IC as a function of time and dt. So this equation can be used if initially you do not have any voltage stored, voltage across the capacitor, and no energy is stored in the capacitor at time t is equal to 0. So in this case, we are taking the initial time as our reference time, which is 0. So these two equations are important. Well, the basic equation is this basically, and from that you can always integrate and you can get the voltage. All right, with that, I think it's 10:30, so we are going to take a break about 10 minutes and then we are going to continue after the break. Okay. So let's say you have a capacitor. And the value of capacitor is 2 farad. You have a current passing, again, we call it passing through a capacitor. Remember, it does not really pass through a capacitor, but generally that's what it is referred to as, passing through a capacitor. And then the voltage. The voltage across the capacitor is given as 2 cosine 2t sine 5t volt. So it's a, it's a time dependent voltage. That's 5t. Sine 5t, yes. And the question is, determine the current at 2.8 second. Determine the current passing through the capacitor. Again, I'm keep saying passing through the capacitor. Remember, it's just a, that's how you say it, but current does not really pass through a capacitor. So basically, what we are doing, we are using this relationship, current and voltage, and then we're going to find first the expression for the voltage, and then we are going to go ahead and plug in the value of time, 2.8 second in that expression, to find the value of current at 2.8 seconds. So that's how we're going to solve this problem. So since the capacitor current is given by C dV, which is a function of time, or dt, okay, when you're taking the differentiation of that expression, who's going to tell me what would be the, what we are going to do to differentiate that? Very good, excellent. So we're going to use the product rule, exactly. We're going to use the product rule. Derivative of A times B is derivative of A, or B times derivative of A plus A times derivative of B. So we're going to go ahead and apply the product rule on this C. And I'm going to bring this 2 outside. So I'm going to just make it 2C because 2 is a constant. And then I'm going to take the derivative of, let's say, sine 5t. So I'm going to put down cosine 2t. And then what is the derivative of sine 5t? Who's going to tell me? Hmm? 5 cosine 5t. So I'm going to put a 5 over here, 5 cosine 5t. And then plus Then I'm going to take the derivative of the first term and put the second term as it is, sine 5t. What is the derivative of cosine 2t? Okay, negative 2 sine 2t. So I'm going to put a negative sign here, negative 2 sine 2t. So this is the expression for the current. And now we can calculate what is the value at t is equal to 2.8 seconds. We can calculate. Let me open my MATLAB. All right. So my T is equal to 2.8. My capacitor is 2 farad. And my current at 2.8 second is going to be, let's see the expression. 2 times C times 5 cosine 2t, 5 times cosine of 2 times t, cosine 5t times cosine of 5 times t, minus 2 times sine of 5 times t times sine of 2 times t. 7.1237 ampere. And I can just copy this in. So that's my current, 7.1237 ampere. So simple differentiation. So make sure just remember this formula. I is equal to C dV over dt. That's a basic relationship in the capacitor current and capacitor voltage. Any question? All right. Let's see. Let me see any problem from the book. It's voltage. Right. Okay, let's do this problem. Yes.
We're writing down or doing it by hand. You want us to put parentheses or make different signify what the time goes?
It's at 2.8 seconds. It's a constant value, right? Are you saying that?
I'm talking about just writing.
like I 2.8
Yeah.
is equal to 7 point.
Yeah. Like that.
Yeah, that's fine. Yeah. Please. 7. Okay, another problem. Let's see. Let's do this. Voltage function is given as on the graph as, let's see, 1, 2, 3, 4, and then t is in second. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. The function is given as a straight line from 3 volt to 1 volt, and this is 4. 3 volt at 0 time and 1 volt at 4 seconds. And then after 4 seconds, it becomes constant. This is the voltage that is given to you across a capacitor. Capacitor value is 1 microfarad. There are two main type of capacitors: electrolyte capacitors, and the other one, that's the one that are thin. What do you call them? Electrolyte and no, you know, the thin one, the one that we have. Electrolyte are the polarized, basically. It has positive and negative. But the other one, forget the name of those. The one that we have with the flat one, you know, ceramic capacitors. Ceramic capacitors, yeah, yeah. Ceramic capacitors, they are non-polarized, and the electrolyte capacitors, they are polarized. Okay, so 1 microfarad capacitor given to us, and we need to find out what is the current. Now, one important thing, remember that the relationship that we discussed, I is equal to C dV over dt, that relationship depends upon the current is entering where the voltage on the capacitor is positive, right? So that relationship is established on that fact. In case if there is some problem that the voltage direction is opposite on the capacitor and the current is entering on the negative side, then you must put a negative sign. I is equal to negative C dV over dt. Remember that. Okay, so we have to find, let's say what is asking. This is a book problem. Current, we have to find the current. Determine the current IT. Now, when this type of problem is given to you, that you have different values of voltages in different time instances, those are generally called piecewise problems. And you have to generally solve them in different pieces. So for example, you have two different values. One value is between 0 and 4 seconds, which is determined by this line. And then it becomes constant after 4 seconds. So you're going to solve this thing in two parts. You're going to solve for the current based upon the line from 0 second to 4 second, and then after 4 second when it becomes constant. So these are the piecewise problem. And whenever you have a piecewise problem, generally you represent the value in during different time intervals. So for example, let me write down here the voltage. we know that the voltage becomes constant 1 volt for time greater than 4 seconds. Now between that, between 0 and 4 seconds, how we are going to determine the voltage? Equation of the line. Yeah, you're going to write down the equation of the line and determine that this is the voltage across the capacitor. All right. So who is going to tell me how we are going to find the equation of that line that you see from 0 second to 4 second? What will be the equation of that line? Chris? Oh, that's a generic, yeah, this is a generic formula, y is equal to mx. So what will be the equation in this case? I'm sorry? Okay, so generally what we write, y minus y1 is equal to, what was that, the slope of the line? y2 minus y1 over x2 minus x1, that's the slope of the line, m, times x minus x1, if I remember correctly, right? Y minus y1 is equal to slope times x minus y1, and slope, of course, is if you have 2 points on the line, then the difference of the values between those 2 points. So in this case, this is my first point right here, and my first point is x value is 0, y value is 3, that's my x1 and y1, and here my x value is 4 and the y value is 1, that's my x2 and y2. So if you write this down, y minus y1, that is y minus 3. In this case, y, of course, is v. So the equation is going to be v, v minus 3 is equal to y2 minus y1. y2 is 1 and y1 is 3. So 1 minus 3, negative 2 over x2 minus x1. x2 is 4. So 4 minus 0 and x minus x1. So x is, of course, time and x1 is 0. So the equation of the voltage is going to be negative half t plus 3. Negative half t plus 3 between 0 and 4 seconds. Right? Any question, guys? Again, we are using basic slope formula to write the equation. And once we have this defined for different interval of time, then you can apply the capacitor current formula. So between 0, 4 seconds, IT is equal to C dV over dt. All right, guys, what will be the derivative of that expression? There again, negative half. So negative C over 2 is the current. And C is given as 1, micro. So negative 1/2 micro ampere. That's between 0 and 4 seconds. And when t is greater than 4 seconds, don't have to do that since it's a constant value, but result is going to be 0 because derivative of a constant is 0. So your current, you want to plot the current, that's what they're asking in the book, plot the current. When you plot the current, let's say negative 1/4, negative half, negative 3/4, 1, 2, 3, 4, 5, 6. So the current is going to be negative half micro. Let me see, this is, let's say, microampere on y-axis and second on the x-axis. So negative half from 0 to 4 seconds, negative half micro, and then it's going to become 0. Yes. 0.5, negative half, doesn't matter. The same thing is a perfect fraction. I mean, right, you know. Now, from this problem, there's one thing that you need to learn and understand very clearly. As you can see, the voltage is changing gradually, finally becoming constant. The current, as long as the voltage was changing linearly, the current is constant, and then became 0. What happened at 4 seconds? At 4 seconds, the value of current changed instantaneously. It went from negative half microampere to 0. Right? However, if you look at the voltage is not changing instantaneously. It is going down gradually and then becoming constant. So one thing is very important to remember. The voltage across the capacitor cannot change instantaneously. It's just not possible because remember, voltage is established because of the accumulation of charges. When you remove some charges or you add some charges, then the voltage value is going to change. Right? Removing charges or adding charges on the plates takes time. So the voltage across the capacitor cannot change instantaneously. So when we solve problems, you will see that we're going to take the voltage just before the change is happening. Let's say you are flipping a switch at time t is equal to 0. So we calculate voltage across the capacitor just before the switch was flipped and just after the switch was flipped. It's exactly the same. That's what we are going to assume to solve the problem. Voltage across a capacitor cannot change instantaneously. However, current can, because as soon as you move any charge, the current is going to change right away. Right? So that's a universal fact. The voltage across capacitor cannot change instantaneously. However, the current can change instantaneously. Another way to look at that is because current is C dV over dt, right? Rate of change of voltage. Let's assume voltage is changing instantaneously in an instant of time. What's going to happen with dV over dt then? dV over dt is the rate of change of voltage, right? If you are taking almost 0 amount of time to change a value, what's going to happen with dV over dt? No, you're taking almost zero amount of time. It's not zero, but let's say you're taking femtoseconds to change a value, right? Let's say voltage change from 1 volt to 1.01 volt in 1 femtosecond. What's going to happen to the current? It's going to be extremely large. It's going to shoot up like no tomorrow, right? Because you're changing your denominator is extremely small. If it is changing in an instant of time, going from negative half to zero, let's say if this is voltage, let's say, right? Then what's going to happen to this term? It is going to shoot up, and this is what we call an impulse. It's going to be like an impulse. It's going to be an extremely large value. And none of your circuit is going to sustain that value, basically. That's like lightning, strike of lightning. When you have a lightning strike, that is equivalent to as impulse function, because a large amount of current flows in a very small fraction of time, a very small amount of time. You have a large amount of current flow, or a large amount of voltage that is between the ground and that place where the lightning has struck. The voltage difference is extremely large in an instant of time. So that's the practical implication of why the voltage across a capacitor cannot change instantaneously. Because if it does, your current is just going to be infinite almost, basically. And that will not be able, your circuit is not going to be able to sustain that much current. So keep that in mind, write it down somewhere. And always remember that voltage across a capacitor cannot change instantaneously, but current can change instantaneously. Okay, let's see. Let's do another problem. All right, let's see if I have some. Grab a problem from the book. Let's see. Let's see, current passing through a capacitor is given by IT. The voltage at t is equal to 5 seconds if initially there is no energy stored in the capacitor. Capacitor value is, let's say, 2 microfarad. The current passing through a capacitor is given by IT is equal to 2 sine 2000 pi t milliampere. Determine the voltage at t is equal to 5 seconds if initially there is no energy stored in the capacitor. Initially means that there is no energy stored, means that initial voltage across the capacitor is 0. So since we have to find the voltage, we use the integral equation that we have. Vt is 1 over c 2 sine 2005. I'm sorry? 2 sine 2000 pi t, yeah. 2 sine 2000 pi t. Oh, no, it's not 25. It's 2 sine 2000 pi t. So we'll determine the voltage. Initial value of the voltage is 0 because there is no energy stored. So we're going to integrate the value of current from 0 to t, write down an expression for the voltage, and then plug in the value t is equal to 5 seconds to determine the voltage value at that. All right, integral of sine 2000 pi t. Who's going to tell me that? I'm going to put 2c here. Integral of sine 2000 pi t. Opposite of differentiation, remember that. Your cosine is opposite, that's true. But what's going to happen with the constant? Say it again. 1 over 2000 pi, exactly. So negative 1 over 2000 pi cosine 2000 pi. And of course, we have t and we have 0. So 2 over c negative 1 over, I'm going to bring negative 1 over 2000 pi outside. 2 and 2000 will cancel out. So I'm going to put 1000 pi c. So 1 over 1000 pi c. Cosine t and cosine 0 is 1. Cosine of 0 is 1. So the expression for the voltage is going to be 1 over 1000 pi c 1 minus cosine 2000. That's what we're going to get. And make sure you check it. Remember, initially there is no energy stored. That means voltage is 0. So at time t is equal to 0, when you put t is equal to 0 over here, then this will become 1 and 1 minus 1 will become 0. So initial value of the voltage is going to be 0. And now we can find what is the value of the voltage at that specific time instance that is given to us. Let's see. It was required 5 seconds. So let's go and calculate it at 5 seconds. So t is equal to 5 and capacitor is given as 2 microfarad. 2 exponent -6. V is equal to 1 minus cosine 2000 times pi times t divided by 1000 times pi times parenthesis is missing. Oh, 0. 2 exponent. Okay, let's change the time so it won't be 0. Let's assume that time is some other time. Let's say time is 2.3 millisecond. Or 2.3 seconds. Let's say if it's works out better. 2.3. Again 0. It's just the cosine is coming out to be 1 anytime you put. Let's see. 2.78. What value should we put? There it's not going to be 0. Any value that I put is the cosine becomes 0. 2000 pi t. That's always giving us 1 for some reason. Why it's always giving us 1? Let's cosine 2000 pi t. 2000 pi. Okay. 0.56 microsecond. 0.56 milliseconds. Yeah, 0.56 millisecond is good. Doesn't give us 1. 0.56 millisecond. Zero 0.56 millisecond. So the result is 307.13. $307.13 at that time. Okay, quickly before we leave, a couple of more things, and then we're going to continue it next week. Let's write down how to calculate the capacitor power. Remember, power is what? Electrical power is the product of voltage and current. And we know that current, the capacitor can be given by C dV over dt. So one of the formula to calculate the power in the capacitor is CV dV over dt. And likewise, in terms of integral, we can put V as 1 over C initial time t naught to t I t dt plus the initial value of the capacitor voltage at t naught times I. So these are the two equations that we can use in order to calculate the power of the capacitor. And the more important thing is the energy stored in the capacitor. So what is the formula to calculate energy stored in the capacitor? Remember, power is rate of change of energy or rate of change of work. dW over dt. Rate of change of work or energy. That's from physics. So to calculate the energy, we have to take the integral of power. Cross multiplication and then integral. Let's say at t naught, the initial power, the initial energy stored was omega naught, and at t, energy is going to be W. T naught. Power can be given by CV dV over dt, and then we have a dt over here times dt. So when we take this, instead of putting T naught and T, we're gonna say that the voltage, because we are now integrating voltage V with respect to dV, the voltage, initial voltage was V naught, and final voltage will be V or Vt. So when you integrate that, power or energy at time t minus the initial value of energy is equal to C, initial value of voltage, the voltage at time t, V times t. All right, what will be the integral of V dV? Integral of x with respect to x is 1/2 x squared, exactly, 1/2 x squared. So 1/2 V squared, C times 1/2 of V squared. Initial value is V naught, and at time t is going to be V. Energy at t minus initial value of the energy, 1/2 C Vt squared minus C. Again, if we assume that initial value, initially the capacitor was at rest, assume no energy is stored in the capacitor at time t is equal to t naught initial time, then no energy is stored, initial energy will be 0, and since there is no energy stored, there will be no voltage difference between the two plates of the capacitor, so initial voltage difference will be 0. So the simple equation to calculate the energy stored in a capacitor at time t if initially there is no energy stored is given by 1/2 C VT square. So this is a very common equation to calculate the energy in a capacitor. W is equal to half CV. So next week we're going to do a problem on this. Before we leave, one thing most of you should know about this, about the combination of capacitors. Not next week, sorry, on Wednesday. We have 4 capacitors, can be any number of capacitors. And if I want to find out what is the equivalent of all these 4, or if I want to replace all 4 by 1, how are we going to find the equivalent? No, not summation. Anybody remember from previous class? Mm-hmm.
The series of is actually the same formula.
Very good, excellent. So series combination of capacitor is the same as the parallel combination. So it's going to be 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C. Excellent. And can be any number of capacitors. And likewise, if you have parallel, then it's going to be the same as the series resistors. If you want to replace all of them by a single capacitor, then the capacitors are going to add instead of the parallel. And this can be proved, of course, using the capacitor voltage and current. I'm not proving it right now, but so remember that capacitor goes opposite of resistor. Inductors are the same as resistors. So inductors, if they're connected in parallel, it's exactly the same as calculating resistors that are connected in parallel, and inductor connected in series are going to be added together to find the equivalent of inductance. So capacitor is opposite of inductor and resistor. So that's where we're going to stop today. It's 11:30. I think everyone is here, right? Nobody's absent. So everyone is present. Once again, I'm not going to post the solution right now. I want you to work on the exam, and then I'm going to post the solution later on.